Okay, so let's determine the average translational kinetic energy of an oxygen molecule at 300 Kelvin. Now I'm going to just do an order of magnitude estimate for you here. You can fill in the details and get the actual velocity, which is a little higher than the order of magnitude velocity that we get here. Okay, translational kinetic energy of a molecule at 300 Kelvin is just obtained as 3/2 kT. And you put that in and you put the value of K, the 1.38 times 10 to the negative 23rd joules per particle Kelvin, and you get 10 to the negative 21st joules, on the order of 10 to the negative 21st joules. You can get the exact or the more precise result yourself. Okay, then 1/2 mv squared is then your 10 to the negative 21st joules, because that's your average translational kinetic energy, and I should put a bar over that to indicate that it's an average. If we know the mass then of an oxygen molecule, we can easily solve for its velocity. Well, the mass isn't hard to find if you understand what a mole is and understand molar mass. The mass of a mole of oxygen is 32 grams, oxygen being diatomic, its atomic number being 16. Then O2 is going to have an atomic or molecular mass number of 32, which means that a mole of it has a mass of 32 grams. Okay, so if we divide 32 grams then by the number of molecules in a mole, we'll get the mass of a single molecule, which is on the order of 10 to the negative 25th kilograms. Okay, it's actually about 5 times 10 to the negative 26th. So whether it's a 10 to the negative 25th or negative 26th is a little bit of a question here. But again, order of magnitude, that's about right. Okay, it turns out then if we solve this using a mass of approximately 10 to the negative 25th kilograms, we double the numerator, divide by m. We're going to end up with something like this, which is on the order of 100 meters per second. Now it's actually hundreds of meters per second because these order of magnitude calculations are not precise. But you see that the oxygen molecules are moving quite fast. That's one application. Another, let's just determine the total translational kinetic energy in 2 liters of a gas, if the gas is at atmospheric pressure. Okay, now we've got the volume, 2 liters, we've got the pressure, atmospheric. The total translational kinetic energy, note I don't have a bar here, I mean total translational kinetic energy, not the translational kinetic energy of one molecule or a sub-collection of molecules, but of all the molecules, is then 3/2 PV. Now if I multiply that out with a pressure of 10 to the 5th newtons per square meter, which is very close to atmospheric pressure, just rounding off a little bit, and a volume of 2 liters, which is 2/1000ths of a cubic meter, a liter being 1,000th of a cubic meter, we very quickly see that kinetic energy is about 300 joules. A total of about 300 joules in that 2-liter empty bottle at room temperature, at atmospheric pressure. Doesn't matter what temperature it's at. If it's at atmospheric pressure, of course that's going to have a lot to do with the temperature. Now we want to take a quick look at where that total energy is, or what the total energy in that bottle is. If it's air in the bottle, we've just got the translational energy, which is 300 joules. That is equipartitioned into equal parts in the x, y, and z directions, as we've seen. So we have 100 joules of kinetic energy in each direction within that bottle. That means that we have 100 joules for every degree of freedom, for every direction in which the gas molecules can move. Now, degrees of freedom means mutually perpendicular or completely independent directions of motion. There are 3 translational directions of motion. independent, and we call them generally X, Y, and Z. They're all mutually perpendicular. We also have rotational degrees of freedom, as we've seen. The molecule can rotate this way, okay, about a vertical axis, an axis that's vertical, assuming the molecule's in this direction, or about this axis. Okay? So there are 2 degrees of freedom. Each one of those takes as much energy as any one of the translational degrees. If all the molecules are sitting still, are non-rotating, all in the same direction, when they start colliding, they're going to get bumped on different ends, and they're going to start rotating pretty quickly. And just like the energy equal partitions itself between the X and the Y direction in the 2-dimensional billiard ball simulation, it's going to partition and fill up these 2 degrees of freedom with 100 joules each. So there's 200 joules of rotational kinetic energy in that 1-liter bottle. So U, what we call the total internal energy, is our 3/2 nkt plus our 2/2 nkt, which is, of course, now big N times little k is the same as little n times r, big R. Okay, nk is the same as nr. We're using big or little n as appropriate. So this is the same as 3/2 nRT plus 2/2 nRT. But there's our 300 joules plus our 200 joules, which is a total of 500 joules of total internal energy in that bottle, in which we have the 300 joules of translational kinetic energy.